right, it is Thursday, April 1st. This is Civil Engineering 481, Transportation Engineering. And today we're going to do a review of chapters 5 and 6 to prepare for our second midterm exam, which is going to be at our next class meeting on Tuesday, April 6th, next week. So that's what I'm going to be covering today. Your homework for chapter 6 is due, I think, tomorrow by 4 o'clock. I just made it for the end of the week. I hope all of you had a good couple of days. The rest and recovery day was the 30th, Tuesday, so we didn't have class that day. And then yesterday was Cesar Chavez Day. So hopefully you were able to get a little rest and recovery in on those couple of days. We have one more rest and recovery day, at least one that coincides with the class, which is April 15th. April 15th is a rest and recovery day 2 weeks from today, so we won't have class on April 15th. So in any event, that's that's looking ahead. And I would also just note that the group papers are due on the 27th of April. It's a little bit less than 4 weeks away. So I don't know, a week or two ago, I put a slide into the class, just describing what a schedule might look like for a group working on a group paper. And then so the papers are due on the 27th, and then the 29th and the 4th, the 29th of April and the 4th of May. The groups will be presenting their papers. So anyway, that's just a look ahead there. Before I get started on the review, any questions or anything that anybody wants to ask or cover before I get started on the review? Okay, before I start going through the slides, just I sent out an announcement with the procedure for the exam, the midterm, which is basically identical to what we did for the first midterm in terms of procedure. It's the same thing. At 4 o'clock on Tuesday the 6th, the exam will post. And it will be pretty much the same format, like 10 true-false questions and then 3 problems that will be related to just only chapters 5 and 6. And it's the same thing. Everything you will need to solve the problems will be provided in the file that you will download or connect to through Canvas. There's no need for anything other than a calculator. You don't need your book. You don't need computers, whatever. You just need your own paper and the ability to upload it back into Canvas by 5:30. I generally go to give you an hour and a half for the exam, an extra 15 minutes just to account for any computer issues, uploading, downloading, that sort of thing. So anyway, very similar to the first midterm. So with that, I will go ahead and start the review. Let me pull up the there we go. And let's go to okay, I'll make this just a little bit bigger there. Okay, let me do one other thing. Let me share something else, just so I'll put it up, and then I'll take it down. I won't show it anymore. Let's see if I can find it. Here we go. You all should be seeing the PDF of the chapter 5 equations, it says there, and the nomenclature for chapter 5. I've been showing this as I've been going through on chapter 5 there. It actually covers a couple of pages of information from chapter 5. Then I've also got the same thing for chapter 6, the key equations and the nomenclature. And I just wanted you all to know that these pages will be provided with the midterm exam. These pages will be attachments to the midterm exam, so you'll have those available. So just wanted to make sure you knew that. So now I'll go back to the slides. There we go. Okay. So going back to starting with chapter 5, obviously, I don't work backwards. I'll start with chapter 5. If you recall, chapter 5 was quite a bit about these three variables or parameters: Q, U, and K, flow, speed, and density. So those terms and those variables are important to understand the concepts in chapter 5. And just to get into, some of the definitions, the flow is defined as the number of vehicles, passing a designated road point during the duration, the time a given time interval. So that's typically vehicles per hour is a very typical way to define traffic flow. And then I put in this slide, not so much for the flow, but just to remind everyone the concept of headway. And headway is a concept of time, not distance, or spacing is the measure of distance. So I think it's important. That's why I have it highlighted here that headway, sometimes it's even referred to as time headway, just to emphasize the fact that headway refers to a measure of time. And then if you recall, we had a homework problem on this, the issue of speed. There's two different definitions. And this is the second of the two definitions of speed: space mean speed, which is the average of all vehicles occupying a given section of roadway over a time period. And then the fact that space mean speed is more useful for traffic analysis. I think it's important to understand that concept. So as I go through these slides, like I did for the first midterm, I try to highlight the things that I think would be helpful for you to focus on as you prepare and study for the exam. Density is a very important concept, and it's density. Oh, I'm sorry, not so much density. This slide I highlighted. Look at the highlighted portion of this slide, and this is where I wanted to emphasize the spacing. It just happened to be on this density slide. Before I talk to you about headway and the fact that headway is a measure of time, spacing is the measure of distance from front bumper to front bumper of successive vehicles in the traffic flow. So just wanting you to be sure that you understand the difference between spacing and headway, because I think headway, sometimes people think at least in my mind, when I hear the word headway, I kind of think of like a distance as opposed to a time headway. So for me anyway. And then this relationship here is, it'll be on the list of equations that will be as an attachment to your exam, but I think just understanding that the relationship of the flow at Q is equal to the speed multiplied by the density. And you can see the units are, vehicles per hour for flow, the speed miles per hour, and then the density is vehicles per mile. So you keep all of these units consistent. But I think it's just a good thing to be aware of, that this is one of the most basic relationships that is that we went over in chapter 5. And it, as you can see here, we've got flow, speed, and density in the relationship. You in this, and I highlighted this figure here so that you understand that this figure has a relationship between speed and density, which is linear down here, and then you've got the relationship between flow and density up here, which is curvilinear, and the relationship between speed and flow over here. So the relationships that flow has with speed and density are both curvilinear, whereas the relationship between speed and density is linear. And so I think that's important to understand, and to just be familiar with this, the relationships that are shown in this graph. So then in chapter 5, we moved on to distribution of as it applies to well, there were some examples we went over that are non-traffic examples, but obviously we wanted to emphasize the distribution of arrivals and departures of vehicles as being important to understanding traffic analysis. And one of the variable distribution relationships that we used was the Poisson distribution here. Again, the equation will be attached to the exam to the extent that you may use it to solve a problem, but it's important for you to understand that Poisson distribution is a way to predict a random distribution of vehicles in our case. Then we also went over this concept called the negative exponential. I know we had homework problems on both the Poisson distribution and negative exponential. And I think it's just important to understand here again that the negative exponential is kind of a specific case where you're predicting the probability of having no vehicles arrive in a time interval t, and so which means that it's the same as the probability of the headway being greater than or equal to that particular time interval. So I think it's a useful tool in being able to calculate various probabilities, as we did in the problems that we worked on that. And so this is the actual equation for the negative exponential. Again, also will be on the attachment for the exam, should you need to use the equation to solve a problem on the exam. So I think that's a concept that's worth paying attention to and taking a look at, and look at the problems that we worked both in class and in your homework on that. Then there's the queuing model components, and those include the arrival pattern, the service and or departure pattern, the number of departure channels, and the queue discipline. So the queue discipline is what referred to the first in, first out, last in, first out, that kind of thing. The number of departure channels obviously just means, if you only have one departure channel, it's going to be, you're likely to be restricted, and queues may very well form unless the arrival pattern is so infrequent that one departure channel works. Sometimes that does, but sometimes it doesn't. And recall, we did some problems where we had a situation where there was arrivals, there was a like a bottleneck, right, where departures were restricted and yet arrivals kept coming. that kind of thing. And so that's where this comes from here. And then this is the where we talked about the queuing model notation, arrival pattern, departure pattern, and the number of departure channels. And we mainly focused on problems that were deterministic, for both arrivals and departures with one departure channel. We did do a little bit in some of the exponential or stochastic ones as well, but if there's going to be a problem on the exam in this queuing area, it's going to be a DD1 type problem, which is very similar to the example problem we did in class 5.7. Can't remember the number of the problem we did for the homework, but I think there was a homework problem that was pretty much in line with these queuing problems. Yeah, here's the example. This is example 5.7 from your book. This is one. I'm not going to go through the entire problem and calculation here, but just to remind you that this is a good one to review. But basically, this is a typical kind of problem. Vehicles arrive at a recreational park. There's a single gate where everyone has to stop, and then the attendant, distributes the brochure, which takes time for each vehicle. So the park opens at 8, at which time vehicles begin to arrive, and they give you the rate, which is in this case, this is a determinate rate. They're saying it's 480 vehicles per hour. After 20 minutes, the arrival flow rate declines to 120, and then it continues at that level for the remainder of the day. So they're obviously making a very, very generalized assumption here that you're going to have this arrival rate of 120 vehicles per hour is going to go all day long. It probably doesn't, but that's a good approximation, and maybe they have a pretty steady flow of vehicles, so it's okay to use a deterministic arrival rate. But the issue here is that you get a big slug of folks that line up at right when the park's going to open, trying to get in early, and they still have to go through that same kind of knothole. And so then they tell you that it takes 15 seconds to distribute the thing. So basically what you do is you set yourself up with the arrival rates, the first arrival rate for the first 20 minutes, the second arrival rate for everything after 20 minutes, and then you match that up against the departure rate. And there can be variations on this. You can have, one arrival rate and a couple of departure rates where, those are the bottleneck questions that we got, where there's an accident and you open it up, not fully, but partially, and then you open it up fully. So it's your departure rates that you have multiples of, whereas you continue to have vehicles, coming into the area. So basically what you want to do is you want to figure out, the number of, and basically what they're saying, they want to know the characteristics of the queue. So you go through you take this information that you put together here, and you end up solving for T, and one of the first things you want to solve for is how long is it going to take to clear the queue. And in this case, if you do the math and you work it out, you end up with 60 minutes. And then you can also, based on that, you can develop, you want to know what the total delay is, the total delay in vehicle minutes. And so you can do that by looking at, this is the graph that goes along with this problem. If you're going to do a problem like this, might not be a bad idea to just rough out a quick sketch. This is the two arrival rates here, and then this is the one consistent departure rate, and the total delay is the area between the two, which you can calculate just by summing triangles and so forth. So that's where you get the 2,400 vehicle minutes there. So there may be a problem on the exam that's similar to this. So I would suggest you take a look at this example 5.7. and the other homework problems that we did on these kinds of problems. So that is chapter 5. That's what I wanted to highlight for you. I'll stop here for a second and see if anybody has any questions about chapter 5. I don't see anything in the chat. So yeah, I will say, how would you go about graphing those type of problems? Well, what you want to do is you look at, for example, the arrival rate. Let me go back and figure out what the arrival rate at the beginning is 8 vehicles per minute for the first 20 minutes. So you figure out, okay, if it's 8 vehicles per minute for the first 20 minutes, how many vehicles are going to arrive in 20 minutes? 8 times 20, 160. So you have the time down here and you have the number of vehicles here. So you put a point 20, 160 right here. Then for after 20 minutes, sorry, I have to go back to the problem. After 20 minutes, the arrival rate goes down to 2 vehicles per minute. Okay, so 2 vehicles per minute. So if you do that, starting here, it's at 2 vehicles per minute. So let's say you go out to, in this case, you haven't done the calculation yet, but you could go out to, if you go out to 60, you just take that. That's a total of 40 more minutes. 2 vehicles per minute. So that means you have to add 80 here. So that's 240 and 60. So you graph, so you've got yourself a point here that you connect with this line, and then a point here you connect with this line, and you just keep it going here. Then you go and you look at what was your departure rate. Sorry, I have to go back and look. The departure rate was 4 vehicles per minute. Okay, so same thing. You say you look out there and you take a look and you say, okay, if it's 4, if it's let's just pick a point here at 30 minutes. If it's 4 vehicles per minute and it's 30 minutes, that's 120 right here. So you take this line, you start at 0, you put a point at 30 and 120, and you draw a line and you keep it going, and you find out where those 2 lines intersect. You could do it graphically, and determine that it takes 60 minutes for the queue to dissipate, or you can do it through solving the problem here by setting the arrival rate here equal to the departure rate, and then solve for t, and then that gives you your t equals 60 minutes. So hopefully that helps you understand how you go about basically you start at the starting point here, and then you go out, you figure out how many vehicles go in a certain period of time. You've got your 2 points, it's linear, and you connect them. And that's, you do that for both the arrivals and the departures. We've had some problems where they say there's a delay for like 15 minutes before vehicles are let in. So that means you have arrivals that start right at 0 and start going up, but the departures don't even start until 15 minutes. It's still 0, and then you put the line in, just as an example. Okay. Any other questions on those queuing problems? And as I said, we did do a couple of problems that had, curvilinear functions associated with them, and did some mild calculus in order to calculate the area between the departure, the arrival and departure curves. But on the exam, I'm not going to go there. I think if there's a problem like this on the exam, it's going to be more linear, like these ones, deterministic and linear. Okay. So I'm headed to chapter 6. I think chapter 6 is a pretty important chapter. I mentioned this before. It goes right to the basics of traffic analysis in terms of the capacity that freeways and highways have. And so there's a few concepts on this introduction slide that I think are important to remember or keep in mind for the exam next week. A freeway is a divided highway with full control of access. Access control means that you can't just, nobody can cut a driveway in directly into the freeway in order to get to in and out can't demand that a driveway be put right onto a freeway that goes right into their line for food. They can't do that, but they can on a local street. How would you get into the in and out if you didn't have like a driveway access off of a local city street? But you can't do that on a freeway. It's access controlled. So freeways theoretically provide uninterrupted flow, right? If they're not overly congested, there's not a major accident or that sort of thing. Generally, freeways provide uninterrupted flow. There's no stop signs. There's no signals to stop traffic. Traffic is only stopped in unusual circumstances, or I guess some people might say, if a road gets congested at a certain time every single day, that's not really unusual. I get that, but that's why I say it's theoretically uninterrupted flow there. And they reiterate the issue of direct access, not granted to and from adjacent property. You have to access the freeway and any surrounding properties through the ramps. Okay, so and then opposing directions are continuously separated by a raised barrier, an at-grade median, or a raised traffic island. And the at-grade median, I think I explained this when I were previously, is that sometimes you can build a freeway with a median that's wide enough that it's okay that you not put a barrier in between to separate the opposing directions of travel. And I think I used an example. If you drive out east on Interstate 8, for example, and you get out into the non-urban areas of that freeway between here and the Imperial Valley, you'll find that there are definitely stretches of that freeway where there is no barrier, because actually there's sections of that freeway, those of you that are familiar with it, that are separated by I think at one point they're separated by maybe over a mile in order to get the two road beds through the mountains there. So in any event. Okay, and the performance measures, these are important for chapter 6, that the freeway segments their performance is defined by 3 things: density, speed, and the volume to capacity ratio. And we didn't spend a whole lot of time calculating the volume to capacity ratio, but that's kind of what, in a sense, what level of service is. But but density and speed we focused a lot on in our problems and so forth. But anyway, these are things that measure or give an indication of how well or how poorly traffic flow is accommodated on a freeway segment. So this is in section 6.2, the concept of level of service, and so density is the performance measure used to define level of service, and you can see a density of less than 11 passenger cars per mile per lane, or less than or equal to 11 is level of service A, which is basically free flow. But if your density exceeds 45 passenger cars per mile per lane, that's level of service F, and that's where you're basically in stop and go congested, into the congested range. And then this is just I highlighted this just so that you understand that level of service A, free flow. Level of service B is basically free flow, but just a few more cars. Level of service C, again, very high performance in level of service C generally, but level of service D, it starts getting, there's enough vehicles that, there can be, maybe some drivers might slow down a little bit and might feel a little bit cramped. Level of service E is definitely on the edge. Basically, it doesn't take much for level of service E to break down into level of service F, which is stop and go, because I don't know, somebody drops a paper bag out of the window and somebody hits their brakes, and then it just has a chain reaction kind of thing. So level of service E is kind of on the edge. Level of service F is stop and go. and level of service A is free flow, and B, C, and D are kind of various levels in between. So that leads us to the key equations that we used in order to define the speed and the flow relationships and, for freeways. These, again, remember, we're talking about freeways first, then we'll switch to multi-lane highways, and we'll do a really short amount on 2-lane highways. So anyway, basically the speed equals the free flow speed in the density calculation if your flow rate is less than or equal to the breaking point. And the breaking point refers to, let me see if I got this. Yeah, the breaking point refers to where these lines come out here and break off and go curvilinear. See, and it changes on freeways. It's with the lower the speed, the further out the break point, right? You can see that here. Whereas for multi-lane highways, the break point's all at the same place. And we'll go over that when we get there. So, but if you have a flow rate that is higher than the break point, but less than or equal to capacity, and you can't be over capacity, you can't have a flow rate over capacity. So if it's in here, then you need to use equation 6.2. The more little, I mean, it's not particularly complex equation, but it just takes a little time to make sure you get everything, all the right values put in here. And so in order to solve equation 6.2, you actually need to use equation 6.3 and 6.4, because equation 6.3 is the capacity calculation that you need to use in a couple of spots. And 6.4 is the breakpoint equation that you need to use in a couple of spots on this equation here. So if you're using equation 6.2, you need equation 6.3 and 6.4 as well in order to do it. And then it leads to this relationship, and this figure 6.2 is the relationship between speed and flow rate, or V sub P down here. And then you've got your densities along these dashed lines here. And then your level of service are the areas in between each of these wedges, I guess you might say. If you consider each of these pieces to be the wedges of a pie, so to speak, that's where your level of service. So there's a lot of information going on in this figure, and all of that is translated into numbers through the table. So it's figure 6.2 and table 6.2, which is very convenient that they both have the same number. For multi-lane highways, they don't have the same number because they're further back in the chapter. But all of that is here, and you can interpolate if you want to get really detailed, using this table, or you can eyeball it using this this figure if you wish, and either is fine. So wanted to just highlight the analysis procedure that we use for freeway segments. You will specify input data. That's basically lining up all your givens in the problem, right? And then you want to estimate or measure free flow speed, and you can use those equations that we just went over. You can estimate and adjust the capacity, and if that's what you need to, if that's what is suggested by the problem, the analysis flow rate, which is the V sub P, if you get that, and then you can estimate the speed. That might be the free flow speed. In some cases it is, in some cases it's not. You have to calculate the speed, and then you calculate the density, which is equation 6.10, which we haven't gotten to yet, but that's kind of the bottom line equation that we're shooting for, which is basically the analysis flow rate divided by the speed. And that gives you, and then once you know the density, you very easily can turn that into a level of service. Wanted to remind everybody about the base conditions that we that in ideal circumstances on freeways, these are the base conditions you'd like to have in some cases. I guess I shouldn't say it that way because it assumes that there's only passenger cars. That's not ideal for the goods movement and freight community. I don't think they don't like the fact that when trucks are restricted from driving on particular roads, they want their trucks to be able to drive on as many roads as possible because it's more efficient for them to get their goods where they need to go. But in any event, the base conditions are 12-foot lanes. Those are the thing. The right shoulder lateral clearance should be 6 feet. If it's more than 6 feet, it shouldn't have any impact on the flow on the right shoulder. Traffic stream is passenger cars only because when you have trucks, they can have an impact on the flow of traffic. So no on or off ramps within 3 miles upstream or downstream of a segment midpoint. Again, ramps can cause friction in the traffic stream, and so base conditions wouldn't have any. Level terrain with grades no greater than 2%, because if you have steep or long grades, they can have an impact. And then this last one's interesting. The driver population dominated by familiar users of the roadway. And I explained that before, that if you have, when people are unfamiliar with the road, they tend to slow down because they're looking for whatever, directions, signs, all sorts of reasons why. I mean, just think about yourself. When you drive, if you take a trip somewhere and you rent a car, and you're driving around, even with all the new apps that tell you exactly where to go and where to turn and so forth, if you're driving in an area that you're unfamiliar with, you just got to be a little bit more careful, probably a little slower, certainly than the person driving right next to you who's driving the road for the 1000th time, right? So just makes sense. So if you're going to estimate the free flow speed, if it's not given to you, you can use equation 6.6. And for freeways, this is the freeway free flow speed equation. And, it basically takes the basic free flow speed of 75.4 miles per hour. Again, I told you a lot of this stuff comes from thousands and thousands of observations over many, many years. And then it's adjusted by an adjustment for lane widths. If you have something less than 12 feet, it's adjusted by the right shoulder lateral clearance if you have something less than 6 feet. And it's also modified by something called the total ramp density, which is a measure of how many ramps there are upstream and downstream, 3 miles upstream and 3 miles downstream from the midpoint of the freeway segment there. And so, so the lane width adjustment, you can see if your lanes are 12, there's no adjustment. But if they're 11, they're 1.9. If they're 10, it's an adjustment of 6.6. And if they're 9 or 8 or 7 or 6, they don't exist, or they shouldn't exist. You shouldn't have a 9-foot lane. Maybe on a city street in downtown area somewhere where traffic is going very, very slow, but it's pretty rare to see a lane width of less than 10 feet anywhere. Lateral clearance, you can see the adjustment factors here. Depends on the number of lanes in one direction, and you have adjustment factors if your right shoulder lateral clearance is less than 6 feet. If it's over 6 feet, there's no adjustment. And then the total ramp density, again, you take the number of ramps 3 miles upstream plus 3 miles downstream, and you divide that by 6 miles to get a number of ramps per mile. So if there's 3 upstream, 3 downstream, that's 6 divided by 6 miles is 1. If there's 6 ramps upstream and 6 ramps downstream, that's 12 divided by 6 is 2. So that's basically how that works. And then this equation is very important. We used it a lot in solving the problems. Equation 6.7, which is the relationship between the flow rate and the hourly volume, it also takes into account the peak hour factor, number of lanes, and heavy vehicles should they exist. As a matter of fact, I think we had one problem that I just got a question about today, where the problem said there are no, it's passenger vehicles only, which is very unusual. As I said before, honestly, the the freight industry doesn't like to see that trucks are restricted from roads, but it happens. And when they do, this adjustment factor turns into 1 because there's no heavy vehicles. You can, when you do the math for it, there's another equation coming up here you can see. So in any event, but this is a very important equation. You're almost certain to be using this in the exam on Tuesday. This is one you may use in the exam. A lot of the problems don't go here on this equation, but I wanted to highlight it. The peak hour factor, sometimes they give you, the problem gives you the information so that you can calculate the peak hour factor, which basically is the hourly volume divided by the maximum 15-minute count within that hour times 4. So it's a measure of like just how how concentrated is that traffic within the hour. And then you've got your passenger car equivalency, or PCE factor. This is where you account for trucks, buses, and RVs, large vehicles. And this is where grade conditions can come into play. Both the steepness of the grade and the length of the grade can come in and have an impact on it. And so there's 2 ways to deal with this. You can have extended general freeway segments or specific grades, and we'll go over both here. And it's important for you to understand both, or to be familiar with both. Extended general freeway segments are where you don't have a sustained, relatively steep grade, and so you can kind of characterize the area that you're analyzing more generally. And so if you're in level terrain, it's any combination of grades that permits heavy vehicles to maintain the same speed as passenger cars. That's level terrain. In other words, you're analyzing a segment, and literally the trucks don't have any trouble keeping up with the passenger vehicles. Okay. And basically it also has this last thing. It says generally includes short grades of no more than 2%. It's generally what they're talking about. Rolling terrain, on the other hand, is a combination of grades and vertical alignment where heavy vehicles do reduce their speeds below those of passenger cars, but it doesn't cause heavy vehicles to operate at crawl speeds, okay, for any significant length of time or frequent intervals. So in other words, yeah, there's a relatively small impact, or smaller impact, on the flow, but not so much that you need to look at the specific grades themselves, and that would be rolling terrain. It's still, there is a factor for both of these, level and rolling terrain, to acknowledge that there are trucks on the road and they are going to have some impact. So if you do have an extended general freeway segment, and the problem will say that it's in level terrain or it's in rolling terrain. If you see those words, level or rolling, you know table 6.5 is what you need to use, okay? On the other hand, when the analysis segment consists of terrain that can't be considered as an extended general segment, then tables 6.6, 6.7, and 6.8 are used to get your PCE values for specific upgrades or downgrades. Now, one thing I would tell you is we didn't do any problems with downgrades. It's interesting, if you look at these tables, there's one line on the table that says for a grade of 0 or less than 0. In other words, downgrades, which really don't have much of an effect, but they do. But still, the fact that there are trucks on there, you can actually still get a value off of, for a long sustained downgrade, you can still get a value for the trucks. If you need to use one of these tables in the exam on Tuesday, it's going to be for an upgrade, because upgrades are the ones that really have more of an impact on flow. Okay. It just makes sense, right? Trucks going downhill aren't necessarily impeding the flow. They still have an effect on flow because there's trucks, okay? People drive differently when there's trucks on the road, that sort of thing. But it's not the same as if you've got a, if they're going up a sustained grade. So I didn't, by the way, I didn't show these tables, but you know, we went over one in class, and they also were in, there was at least one problem in your homework where you had to use one of these three tables. And I'll just tell you, if you do have a problem on the exam, I'll probably just give you the one table you need, because these three tables are based on the mix of trucks, whether they're 70-30, 50-50, or 30-70 between those single unit trucks and tractor trailers. And so I will give you just the table that you need to solve the problem. So for example, if the problem has a 50-50 split between the trucks, that's I'm pretty sure that's table 6.7. So that's the table that you'll be given as part of the exam. Okay. Then there's the heavy vehicle factor, which is in that equation 6.7 that we went over a little bit earlier here. So this equation you're likely to use. Oftentimes you're given this proportion of the heavy vehicles, or if you're not given the proportion, you're given, I think one of the homework problems it said how many passenger cars, how many and how many trucks there were. They might have even separated the trucks into the single unit and the tractor trailers. So you got to add all those together to get your total volume. But then you take the number of those, the number for the trucks, and divide it by the total volume to get this proportion of heavy vehicles. Oftentimes it's given to you, problem. And then E sub t, that's the thing that you get from it's either rolling or level, and you get it from table 6.5, or it is a specific grade that you need to assess, and you have to use table 6.6, 6.7, or 6.8 in order to be able to put that in. And then ultimately, this is the equation that we're kind of aiming for, which is the density calculation, which is the flow rate divided by the speed. And remember, the speed could be the free flow speed in some cases, but if it's not, you need to go beyond the free flow speed and use those additional equations, and then calculate what the speed value is, so that you can get an accurate density, and then you can use that density to be able to determine the level of service for that particular freeway segment. So I'm going to end the freeway portion of this by just saying your example problem 6.1 and example problem 6.2 are good problems to just take a look at. The first one has general terrain. So you're using that table 6.5, and example problem 6.2 has a specific grade that you need to assess. So it uses one of those three other tables. I can't remember which one, but those are good problems for you to take a look at to help prepare yourself for next Tuesday. So now I'm moving on to multi-lane highways. Any questions on the freeway portion before I move on? Okay. All right, so multi-lane highways have some similar characteristics to freeways. Some of the equations look very similar, but they definitely, again, this is all, empirically based research that's been done over thousands and thousands of miles of roads over many, many years. And they have found that multi-lane highways do have different characteristics and do perform differently in some very important ways than from freeways. Even though some multi-lane highways are very high levels of service and allow vehicles to get through pretty rapidly, etc. So anyway, the posted speed limits are generally between 40 and 60 miles per hour, so obviously less than freeways. They usually have 4 or 6 lanes, because if we're saying multi-lane highways, by definition there has to be at least 4, right? I guess 3 could be a multi-lane highway, but even then, that's just a passing lane. That's probably still a 2-lane highway. So got to have at least 4, sometimes 6. And I mentioned before, there are some multi-lane highways that have more than 6 lanes. It's possible. And then they often have physical medians or 2-way left turn lanes. And I had some questions earlier today about 2-way left turn lanes. If you do have a 2-way left turn lane separating 2 sides of a multi-lane highway, that's basically a divided highway. Whereas, as I have highlighted here in green, multi-lane highways can be undivided. An undivided multi-lane highway means that you've got, typically that's a multi-lane highway that's just got a double yellow line down the middle. And, the opposing traffic is passing right next to each other. Or maybe sometimes you'll see, maybe 2 sets of double yellow lines that are separated by a few feet in between them, which kind of acts as a median. But generally, the undivided means that you've got just that single double yellow line. You'll find multi-lane highways mostly in suburban communities and or high volume rural corridors. A lot of rural corridors just are connected by 2-lane highways because there's not necessarily a whole lot of traffic between them. But suburban communities very common to use multi-lane highways. And then traffic signals definitely are found along multi-lane highways. So the equations for multi-lane highways, now these equations look kind of familiar, right? I mean, this is the exact same equation except for how it's modified, right? The analysis flow rate here says for freeways, it's if this is less than the break point, less than or equal to the break point. Well, for multi-lane highways, the break point for all speeds is 1400. In passenger cars per hour per lane. 1400 is the same for all. And when I show you the figure, you'll see that. On the other hand, if your flow rate is higher than 1400, but less than or equal to the capacity, then you need to use equation 612 rather than equation 611, because you've got to figure out where the speed is on that curvilinear portion of the curves. And so and in order to do that, now what you need, the only additional equation you need is equation 613 in order to calculate the capacity. And this is for anything between 45 miles per hour and 70, where the free flow speed is in between those 2 figures. You figure out the capacity and you plug that into the equation here, and you can solve for your speed. You can adjust your free flow speed and solve for your speed that way. And remember, for the freeways, you also had to calculate the break point. But here you don't need to calculate the break point because there it is, 1400. It's already in the equation. Okay. So this is figure 6.4, which looks an awful lot like figure 6.2, but it's for multi-lane highways, and it's not the same. Here's down here is the flow rate, 1200, 1600, so go right in the middle. And sure enough, that's right where the break point is all the way across. There's a break point at 1400 for all of these free flow speeds, 70 through 45, okay? And otherwise it's the same. You've got the speed here, you got the flow rate here, and then you've got the density in these dashed lines here with the levels of service in between the wedges of the pie, so to speak. And there's also a table 610, that is, what you see in this figure is represented kind of in tabular form on this table 610 here. So you can use either one to be able to help you solve various problems. So now the free flow speed for multi-lane highways, again, looks kind of sort of similar to the freeway, but to the freeway equation. But when you look at it more closely, you see this factor here is exactly the same. You use the same table and everything, table 6.3. for the lane width adjustment. There's no difference there, but the lateral clearance is different because you've got to look both to the lateral clearance to the left and to the right in order to come up with this factor. This factor is about the median type. It's a really simple table. You either have a median or you don't. And if you don't have a median, you put in a factor. If you do have a median, your factor is 0. Because if you have a median, you don't modify the flow. And then there's an access point frequency. And here, this is a number of access points per mile. That's the final factor here. And the other thing I just wanted to cover is this BFFS. Generally, this is defined in your book. It's defined as 5 miles per hour over the posted speed limit. Sometimes problems will just tell you what it is. Sometimes they'll tell you what the free flow speed is or the posted speed limit, or they'll just say the speed limit. And so the BFFS would be 5 miles per hour above that. So that's an important adjustment to be aware of there. So I'm not going to show you the lane width adjustment because it's the same as the freeway. But for this total lateral clearance, there's actually this equation 615 here. You have to look at the lateral clearance on the right and the left. And so it's important to show here the total lateral clearance is the sum of lateral clearances of the median. If the median is greater than 6 feet, you use 6 feet, okay? And the shoulder, if it's greater than 6 feet, you use 6 feet. Therefore, for the purposes of analysis, total lateral clearance cannot exceed 12 feet. If you have 12 feet of lateral clearance, let's say 6 and 6, whether it's a 4-lane highway or a 6-lane highway, it's still going to be 0. Okay, but there was an example of a problem that had a two-way left turn lane, which by definition is going to be over 6 feet in width. So you use 6 for the two-way left turn lane, and then there's a 4-foot lateral clearance on the right. So 6 plus 4 gives you 10. So and I can't remember. Well, it doesn't matter whether it was 4 or 6 lanes here. It's 0.4 either way. And so 0.4 was the value used for TLC. Excuse me, not TLC, but for the factor, the TLC factor. Okay. Then we've got this is the easiest table you have in your entire book. If it's an undivided highway, the adjustment's 1.6. If it's divided, it's 0. Pretty simple. Access frequency. This is the number of access points per mile. And so you add, this is a given. I mean, unless you have a map and you have to count them up yourself or something, but generally they'll tell you how many access points there are. They may tell you that there are 50 access points spread out over 2 miles. So you have to do math to just say, okay, that's 25 access points per mile. And so therefore you're in here, you're between, and you can kind of interpolate. If you end up with 25 access points per mile, it probably makes sense to use 6.25 as your reduction in free flow speed there, just as an example. Okay. So multi-lane highways, how do you go about solving them? You calculate the analysis flow rate, same as for the basic freeway segment. You use that same equation, 6.7, I believe. You use the heavy vehicle factor. You use the same formula in PCE tables as for freeways. When you do in that 6.7, you use the same thing there. You calculate the density in the same way, the analysis flow rate divided by the speed, and you can determine the level of service not only by doing you can use either table 610 or figure 6.4 in order to get your level of service. Those are these, where are they? That and that, those two. So that was multi-lane highways. Let me stop there for a second and see if anybody has any questions about how they are different from freeways. I would tell you, you're going to see definitely something on the exam for both a freeway and a multi-lane highway. So understanding the differences between them is good thing to look at. Okay, the final thing I have to go over here is just a couple of slides on two-lane highways. If there's anything on the exam about two-lane highways, it's going to be in that first kind of like true-false section, just so that you understand some really basic concepts about it. Obviously two-lane highways, one lane of travel in each direction and typically undivided. There is, well, the last bullet covers that. Anyway, they generally used for lower traffic volume situations. Obviously, there's only one lane in each direction, and free flow speeds. Interesting here. Actually, they show the range they show is a little bit higher than multi-lane highways, and that is because a lot of two-lane highways are out in more rural areas. They're connecting up, different vicinities and so forth, and they generally do have a low traffic volume. So higher speeds, as long as you can provide the appropriate design parameter, design features, you can safely drive these roads at higher speeds. But the design standards are very wide ranging because of all sorts of things, not the least of which is terrain. And they can have traffic signals, and some of these two-lane highways definitely have stop signs at various, when there's a small community that you come up to, it's not uncommon at all to have a one or two stop signs in the main part of the small town. I'm sure you all can think of places like that. So, and then, there's always a joke about towns that there's one signal in town, some of these small towns, right? Then some towns have one stop sign. So, but in order to pass a vehicle, the opposing lane must be used, and that's a big issue, unless there are passing lanes. And if you have an extra lane, two lanes going in one direction on a road up a hill to allow for passing because there's slow trucks or whatever, that's still considered a two-lane highway, even though there might be three lanes right there. It's still a two-lane highway because you're not adding that second lane for it's a relatively short distance to allow for passing. And so I've highlighted a couple of things here. If you're going to start thinking about level of service for two-lane highways, you have to consider the highway in both directions rather than one direction like you do for freeways or multi-lane highways. And that's because the passing, the thing is if you terrain, as it says here, terrain can have a significant effect on the level of service, because if there's restrictions on passing site distance, that means more and more vehicles are going to turn into a train of vehicles that are following. And if that stays, that situation persists for too long, people start taking chances to pass in areas where it's not appropriate to pass. So that's where that's an important concept in two-lane highways. So I believe that was my last slide. It was. Let me go ahead and. So that's what I wanted to cover today. I think if you go through that and look at some of the key problems we worked in class and you worked on your homework, you ought to be very well prepared for the exam on Tuesday. And again, the exam will be administered basically identically to the first midterm exam we did, a few weeks back. Anyway, I would suggest that you all just kind of take a look at this material, the problems we worked, and you should be well prepared for Tuesday. So any questions before we break up for this evening? Okay, everybody, have a good weekend. Good luck with the studying and so forth. And I will see you all. And remember, I'll be on the Zoom. I'll send out a Zoom invitation. I'll be on throughout the exam, but there's no need to connect unless you want to, or if you have a question or whatever. I'm just there to be available throughout the exam. But generally, the exam will post right at 4 o'clock. You can get started, and once you've completed it, upload it, and then you'll be good to go. All right, thanks everybody. Have a great evening and a good weekend.
Hey, Professor.
Yes, Kyle.
I had a question referring to the specific grade tables. I think it was 6.6, 6.7, and 6.8.
Yes.
So in one of our homework problems, we got percentage of heavy vehicles was like close to 20, but not exactly.
It was close to
That
what? I'm sorry, you didn't hear that.
It was close to 20. It was like 19 point something.
Oh, the percentage of heavy vehicles was close to 20. Okay.
So that would mean we would need to interpolate, right? We can't just say it
Yeah,
was 20.
I mean, I think it. Yeah, I mean, you could just take the number that's. I'm just going to pick. Let's just say the grade was 2%, and the for a percent vehicles of 15 is 2.04, and percent vehicles 20, it's 1.99. If it's 19%, yeah, I would take 4/5 of the difference between 2.04 and 1.99, basically, is what I would do.
Okay, cool.
Yeah, just frankly, I'm not looking for some elaborate calculation to interpolate. I'd be even an estimation to say, look, it's closer to the 1.99 than it is to the 2.04, so I'm going to use 2.0.
Okay.
That would probably be fine. I'm not trying to test your interpolation skills. I'm just more focusing on, do you know where to go? Do you understand how to set up and solve the problem, and know to go to the table in the first place?
Okay, yeah. So basically, anytime we get a value that's not a given value on the table, we at least need to make an estimate of what the value is.
Yeah, I think estimating the value is fine. I mean, but at least, I mean, on the other hand, the example I just gave you, 2.04, I'm looking at table 6.6, 2.04 and 1.99. If all of a sudden you go, yeah, I estimated 3.5, well, I'm going to be like, well, I'm not sure they really, that's not even close, and
Yeah.
So they were obviously in the wrong spot on the table. So just, if you put something in the problem that says, estimated, because sometimes these problems don't match up with an exact number from the table. That's for sure.
Yeah.
But that's fine.
All right. Thank you.
Okay, no problem. Thanks.